1, 2, 1, 2. Jeg venter på at høre lidt. Og jeg kan ikke høre noget her. Jeg kan ikke høre noget. 1 springer meget højt op, den her. Springer meget højt op. Ja. 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 Og den er lav. Meget høj, synes jeg. Jeg synes, den er meget, meget høj. 1, 1, 2, 1, 2, 1, 2. Kommer der noget ud her? Det gør der.
Yeah, to start.
Yeah.
It's okay?
Yeah, for me it's okay.
Okay.
Yeah, 1, 2, test. 1, 2, test. 1, 2, test. 1, 2, test. Test, test. Yeah, okay. I assume I have the full 25 minutes to speak.
30 minutes. Okay,
Oh,
20.
yeah, can I speak 30 minutes?
Look, you have the whole time for 30 minutes, so I would suggest speak for 25 in case you have some questions, things like that.
Yeah,
So
but
I would suggest.
yeah, I have to see a little bit because I reversed, no, I rehearsed
Okay, so
presentation and I came at 36 minutes when I want to say everything. So
no,
I
try to squeeze it to
yes,
25,
so
something like that. Okay, in case you extend a little bit more, there's no problem. I think that we can.
yeah, but I intend to keep it under 30 minutes.
Okay.
Absolutely.
Okay.
So I'll start this one already.
When it's green, it's ready.
Dear all, welcome. Good afternoon. I would like to welcome you all to this TNC2007 and this first session, first day of the Terena conference. As you already know, this session is labeled as quality infrastructure end-to-end. As all the sessions in the TNC, it has three presentations. Totally different presentations between them, let's say. The first one that will be presented to you by Dirk Janssens from the University of Leuven in Belgium. It's about an enhanced Linux, let's say, kernel in order to provide some quality of service and other services to the academic users of his university, if I'm saying correctly. After that, immediately, Vangelis Chaniotakis will present a very nice work that has been done in the context of some Greek project and also in the context of the GN2 project. This work tackles mainly issues relating to the provision of quality of service in big networks, how you can how issues about interoperability are tackled, etc., etc. And last but not least, Vasily Kipouli from the National Technical University of Athens will give you a presentation about SLA-related issues and how those things can be monitored in such networks for many reasons, just to name a few of them, for grid infrastructure and things like that. So we have three presentations, more or less 30 minutes for each speaker, including some questions that we might have at the end. So we can proceed immediately with the first presentation. Dirk, you can give the floor to Dirk. So Dirk, welcome and please.
Good afternoon. I will have a little talk about BCrouter. It's a software project we developed at the KU Leuven. A little overview. I'll talk about how did the project start, what the main features are. I give some examples of the features. A little overview of the implementation, how it is done. Little performance figures, because it's already in production. It works for 2 years now, and some future plans. How did it start? At the KU Leuven, there's a project called COTNET. The goal of COTNET is to connect KU Leuven and associated high school students and personnel to the campus and to the internet from their homes. There's a possible user base of about 70,000 students and about 10,000 personnel. The reason for the COTNET project is to enhance the possibility of study and research in an academic environment, and a very important element is the low entrance fee and the cost for the students. In general, students don't have much money, but they like to be connected. So, therefore, the university owns a lot of student dorms. That accounts for about 5,000 connections. And there is a corporation with 3 commercial service providers. COTNET is used on a daily basis by approximately 30,000 different users. The COTNET project started in 1995 and evolved and grew and grew. And in 2003 there were some performance problems starting to arise. On COTNET there is, everybody has to log in to the network, and there is a quota system. Every user has 4 gigabytes quota a month. But the old system that was designed in the late 90s was maxed out. It consisted of 2 Cisco 7500 routers. And we needed more flexibility for the bandwidth and quota enforcement. The current solution at the time was rather limited. So we redesigned the network from scratch, and we started with what do we need, what do we want from the network, without any technical specifications at that moment. There were 3 basic requirements. No anonymous access to the internet, so we needed a form of network authentication. Each user is only allowed a certain amount of gigabytes a month traffic. So we also need the network quota enforcement. And we also want to prevent that a few users would consume all available bandwidth. Because, yeah, if you have no rules at the network, students are very inventive in consuming bandwidth. So the network bandwidth regulation is also a very important part. There are also some extra requirements. Sorry. Only KU Leuven users can access the KU Leuven network. So students from an association can get onto the internet, but cannot access directly the KU Leuven network itself. So there has to be some user group differentiation possible. First part, the authentication. So, yeah, I already told it. All users must authenticate before they use the network. It's done by being so, yeah, most user-friendly way we could think of. If you are on the network, you're not logged in, you open your browser and you're automatically redirected to a login web page. There are also powerful exceptions possible, so even if you're not logged in, it's possible to get to certain necessary sites, for example, software update sites, educational sites. You mentioned it, it's possible. The clients itself, yeah, due to the web-based login procedure, there's no extra software configuration needed. There is also a quarantine system. It's currently in development. It means that if somehow a user is administratively blocked on the network, for example, we have some proactive virus detection, and if we suspect a PC has a virus, the PC cannot log in anymore, and the user is redirected to another web page where he sees the reason why he is blocked and some helpful tips. So it automatically restricts network access if a user is administratively blocked. The authentication itself is done on a separate web server, but once the user is authenticated, the login web server tells to BCrouter that user is logged in on that IP address. So BCrouter knows the connection. And yeah, he uses that information for quota and bandwidth management. Quota and bandwidth management, it's done both on user and IP level at the same time. I think that's something not found in most commercial devices. I can't think of any commercial device, in fact. The quota check is real time, so for every packet that is passing the router, it is checked if it is allowed to pass. So it's not like some other hardware routers where only the first packet is checked against an ACL, an access control list, and the rest of the flow is just on hardware with no checks. So every packet is checked. Every user and IP address can have its own individual settings. So, for example, you can make a difference between a personal PC or a lab PC. You can have limited guest accounts. They all have their own setting without any performance impact on the router. So, suppose if a user is using too much of his quota and he is using so much that his quota will be exceeded, the user is not blocked from the network. His bandwidth is throttled down in a way that he never can exceed his quota. The next slide will go more into detail about that. But that also means a user who has no quota left, he's on a kind of small band. But if he stops downloading for a few minutes, the user can immediately use again the quota he has gained during the time he was idle. So we can use that again at normal speed. Several commercial solutions and service providers, they calculate it once a day, or sometimes it was even once a month. But this is kind of real-time small band. Also, it was very important to have the capability of powerful exceptions to both quota and bandwidth checks, because there are always sites that need special treatment. The main principle behind the algorithm is based on the leaky token bucket principle. I don't know if many of you ever heard of it, but you can imagine a bucket of water. This is the bucket. In this case, it's half full with water. It is filled at the top with droplets. I call them tokens here. And it is filled at a constant rate. So day, night, doesn't matter, the rate is constant. At the bottom, the bucket can be drained. And the rate of draining depends on the amount of network packets that is entering the router and that belong to the bucket, if you can say so. The policing algorithm, this is some software code, tries to give each packet a droplet of water. So you can see this packet has one, this doesn't have one, doesn't have one. And at the end of the router, before the packets leave the router, the packet stream is filtered so that only the packets that have a droplet on them can leave the router. The other packets are dropped. There is a certain maximum draining rate. So it's called the burst rate in this case. It specifies the maximum amount of droplets per second, of tokens per second, that can be pulled out of the bucket. So it is used to set a certain maximum speed a user can obtain, or a bucket can obtain. Okay. The normal case, the bucket is filled with tokens. One token is equivalent to 1 byte on the network. So there's a nice one-to-one match. It doesn't have to be, but in this case it is. And the main configurable options per bucket system, in fact, are the maximum size of the bucket. So it's the maximum number of tokens that the bucket can contain. If any tokens are filled, are put into the bucket after it's full, the tokens disappear. They fall besides the bucket. It's the equivalent to the network quota in bytes. Then you have the mean fill rate of the bucket. So it's the number of tokens that is entering the bucket. It's constant. And you can call it the refill speed of quota. Then there is the burst rate. I already told it. It's the maximum number of tokens that can leave the bucket per second. So it is equivalent to the maximum speed. But a simple bucket, so the way I just explained it, has several major drawbacks. We tested it in the beginning because, it was a project that started from zero, and it didn't work at all. The quota worked, but the connections were when you had several simultaneous connections, there was connection starvation, and that's not what you want. So we enhanced the policing algorithm. At the moment, the policing algorithm tracks individual flows that go through the bucket. So it's a kind of connection tracking, a very simple form of connection tracking. This connection tracking is used to prevent connection starvation by distributing the individual bandwidth across the individual flows that go through that bucket. So if you have, for example, a fast download from a file, and you have an interactive session, your interactive session is not killed or does not time out due to the download. Also, the enhanced policing algorithm takes care and calculates the average packet size for each flow, and it uses the average packet size to decide which traffic will be affected first when it needs to drop packets because the quota is too low or you want to obtain a speed that is too high. So bulk traffic is normally a large packet size, so drops will occur first with large packets, and that means that interactive traffic will go through unmodified. It also allows dynamic regulation of the individual bandwidth, for example, of a user based on specific criteria. So suppose there are several users on a network segment, but it's over allocated, and in the evening, when every student wants to use this connection, the network gets saturated. BCrouter can detect when the network level goes above a certain threshold, and if it reaches that threshold, it can reduce automatically the burst rate of all users and IP addresses on that network, so that the speed on the network is artificially shaped just below the saturation level. So you have a kind of controlled dropping of packets instead of, the packets are dropped by the network itself. When saturation is done, or when the total amount of traffic is below a certain threshold, it can increase the burst rate again. So it can be done automatically. Another thing that's still in development, when you just drop packets from a connection, the packet has to be retransmitted. We don't want that because a retransmission is in fact a waste of bandwidth, because the packet was already there, we dropped it, it has to be sent again, while perhaps there are ways it doesn't need to be resent. You can control the retransmits by adjusting the TCP window size of the flows that go through a bucket. Without the adjustment, it's approximately 10% overhead. So if you have a connection that is, with no restrictions, 100 kilobytes per second, you restrict it, for example, to 10 kilobytes per second. There is 10 kilobytes per second leaving the router towards the user, but at the entrance of the router, there is approximately, you see, 11, 12 kilobytes per second, because that's also the retransmitted packets that are counted there. But with the window size adjustment, it is significantly lower, the retransmits. This is also a technique used by some commercial packet shapers. So the conceptual packet flow, because I just talked about buckets, but what's a bucket? How is it related to a user upload, download? When a packet enters the router, the code first determines if it's a download in download direction or upload direction. For example, download direction. it goes to the bucket belonging to the user that is logged in on that IP address. And the entire evaluation is done on user basis by the user download bucket. Then it goes to the IP bucket, the IP download bucket. Also, the entire evaluation is done. And then it goes to the last part of the code where the filtering is done. And if the packet is accepted, it's passed through the router, it goes out on the wire again, and all calculations are finalized for both buckets. If the packet is dropped, nothing happened and the buckets remain in the same state. So at the end, everything is recalculated what has been affected. Same for upload direction, just follows another path with different buckets. So each bucket you see here is completely independent. And every user has 2 buckets, and every IP address on the network also has 2 buckets. So what does this mean and what can you do with it? For example, you can assign a user a quota of 1 gigabyte, refill the quota at the rate of 1 gigabyte a month, and you set no maximum speed limit. For IP addresses, you set a quota of 10 megabytes, you fill the quota at the rate of 5 kilobytes per second, and you set the maximum speed of, for example, 20 kilobytes per second. The result of this is the user settings are determined, are used to determine the maximum volume a user can download each month. So if a user logs in on PC A, all his traffic is accounted to the 1 gigabyte of the user. If he goes to a PC B, the traffic he generates is also accounted to his user bucket of 1 gigabyte. But the IP settings determine, in this case, the real-time bandwidth usage. So the PC where he is working on never can reach more than 20 kilobytes per second. For the first 10 megabytes, if he has exhausted this quota, he can still work at the rate of 5 kilobytes per second. If he, for example, stops 10 seconds with generating network traffic, the bucket is filled 50 kilobytes, 10 seconds, 5 kilobytes, so it's 50 kilobytes. He can use that 50 kilobytes again at the normal maximum speed. Buckets are re-evaluated every 10 milliseconds, so it's pretty real time. Second example, we assign the user unlimited quota, maximum speed of 50 kilobytes per second. IP settings are the same as the previous slide. The change is if a user logs in multiple times on the network, for example, 3 PCs, the sum of all logins cannot exceed the maximum user speed of 50 kilobytes per second. And that speed is divided across all the hosts where the user is logged in. And each individual PC still has the restrictions imposed by the IP settings. Something about the exceptions I talked about in the beginning. The exceptions work with kind of flags. So you have an IP speed limit flag. If it is set, the IP speed limit is respected. If not set, it's not taken into account, and the IP address can have kind of unlimited speed. Same for user speed limit. IP accounting is to tell if a packet is accepted, should it be subtracted from the IP bucket or not. Same for user accounting, and there's one flag that specifies that no login is required. These exceptions can be made for hosts or even entire networks. It's no problem, both local or internet. some examples, say your default network policy is you require a login. All quota is accounted to both the user and IP addresses. And you specify traffic must obey both user and local IP speed limits. But there are embedded devices that can't log in and still need network access. For example, printer servers or something. So that's localhost A does not have to log in to access the internet, but it still uses IP quota and speed settings, just flipping the right bits from the exception word, and you can achieve this. Same way for traffic from an internet host B is always possible from any local host and is never accounted, but the local host IP speed limits are still obeyed. For example, a website with security patches, it's also something that's possible just by setting the correct flags. So any combination of exception flags is possible in either direction. The routing part, so yeah, it's a router. So there's also a DHCP helper, which allows forwarding of DHCP broadcasts to a certain DHCP server. So if a client sends a broadcast on the network, but the DHCP server is company DHCP server that has no connection to each individual network, the helper will see that the broadcast and forward the request to the DHCP server, and the client gets an address. Also, the possibility of DHCP auto logout. If you set the DHCP renewal rate, for example, at 10 minutes, BCrouter is aware of that, and if he doesn't see a renewal packet, he can log out the user automatically. For example, if a user forgets to log out or doesn't log out and turns off his PC, the user will be automatically logged out. Then there is user group-based routing that was needed to differentiate between Karl Löwe users and other users. So each user group has different routing tables that are independent of each other. So you can have a normal user, a quarantined user, a visitor, all have their own routing tables, and you can do whatever you want. Implementation. BCrouter is a software project. It's a part in, it's a Linux software project. A part runs in kernel space, a part runs in user space. The kernel space is a net-filtered framework module called IPT BCrouter, and it implements an IP tables target called BCrouter. I don't have time to explain what netfilter exactly is, but I assume some of you understand it. It requires a 2.6 kernel, and all packet processing is done entirely in kernel space. So there's no need at all for slow kernel user context switches where the server has to switch between kernel mode and user mode. And there's also high performance network logging capability that also runs entirely in kernel space. Unlike traditional syslog ways of logging, this is at least 100 to 1,000 times faster. In user space, there is a daemon that listens to a network port you can connect to and give commands to BCrouter, for example, to log in, log out users, get, set bucket status, and so on. And in user space, there is also the DHCP FWD software packet. That's an existing solution for forwarding DHCP broadcasts. So performance, I'm running out of time. So in use for more than 2 years on COTNET. At the moment, there are 45,000 users in the database, over 100,000 IP addresses. Bandwidth peak at this moment is more than 500 megabits. This is a 30-minute average, so it fluctuates a bit. And BCrouter is the endpoint for 140 network segments, so it has one interface with 140 VLANs coming on it. Hardware, it's one active server with a hot standby. It's a dual Xeon 3.2 gigahertz with a gigabyte RAM. And at peak moments, CPU load is 45%, where 85% of those 45% is spent in the general Linux routing code. And only 15% in BCrouter code. So you can obtain higher speeds if you do some optimizations. The entire system includes the entire BCrouter database, which is also in kernel space, and is approximately 300,000 bucket systems, consumes 430 megabytes of RAM. The future, we would like to provide or work to a kind of campus network in a box, where we provide a modular open source solution, where BCrouter itself is the core element, where you have a simple web-based user front end, where the user can authenticate himself and see individual login and network usage statistics, both real-time and historical, where there is a log processing backend. The backend that processes all logging that comes from BCrouter, and also stores it in a way that the front end can access it. And also a help desk and management website that is a little more technical, and where you can diagnose problems and view the network more in technical detail. The moment status, I'm further developing BCrouter. You have seen there are a few items in development. And design of the log processing backend is also at the moment a priority. There is already proof of concept, but it works and it shall work, but it still needs a lot of programming. So in the end, BCrouter is a solution that provides network authentication, user and IP quota enforcement, and user and IP bandwidth management. Those are most important requirements we had. It's a kernel module, and the future of BCrouter is network in a box. But that's still a long way to go, but we will get there. So if there is time for a few questions, I don't know.
Thank you very much, Grit. So are there any questions? Please. Yes, of course.
Thank you. Grigoris again, Armenia. Let me ask you 3 questions. Is it possible? Yes. Okay. Is it possible to pass through multicast through your router?
Not at the moment, but it's something, if it's needed, I can look at it and see if it's easy to implement, but at the moment, not.
Okay. As I understand, your network after this router is only L2.
This?
One side of the router is your internet.
Yes.
And after the router, you have only L2 level switch.
Yeah, BCrouter is the only layer 3 device.
Only layer 3 device in the whole network?
In the whole network, yes.
What about broadcast storming?
You can, yeah, there are also some layer 2 switches between the actual user.
They are preventing.
Hmm?
They are preventing.
I do not.
They are preventing these layer 2 switches.
Not at the moment, because we don't have any problems with it, but it can be.
They are not manageable switches.
Yes, they are manageable, but there aren't any broadcast storm protections enabled at the moment. But if it should be needed, it can be enabled there, as close as possible to the user. Or you can use some filtering in Linux before, as soon as a packet enters the router, you can already do some filtering. So it's even before the packets are routed or further processed by Linux. And in that way, you can have a very performant filtering.
It's a 1 gigabit Ethernet after the router, yes?
Yes.
1 gigabit. And last question, sorry for such a quantity of questions. What is the efficiency of this system if you compare with the network without such router? Thank you.
Well, it's already in use for a long time. All users know they have 4 gigabytes a month quota. So it's already embedded in the student culture that they have to account for their 4 gigabyte limit. So it's not easy to say how it's at the moment if we should turn it off. But in the beginning, we saw, I think, it's a few years ago, so the network traffic dropped in half immediately. So in the beginning, there were a lot of users who were hitting their quota because they didn't know better, and but at the moment they changed their behavior, which is the way we want it. So if the user changes his behavior, that's excellent, we think.
Thank you. Are there any other questions?
Just a couple of questions from different areas. First of all, you said that BCrouter can track individual flows.
Yes.
How the flows are distinguished?
The flows are distinguished by source IP address, source port, destination IP address, destination port. So that's all.
Okay.
That's just made into a long word, and then it's hashed into a smaller value.
Okay, and then does BCrouter work, or are there any plans to work with radius authentication? Because I take it now BCrouter uses some proprietary or homegrown database of users.
Well, the authentication itself is on a separate website. This BCrouter itself does not need an authentication backend, because the website where the user has to authenticate, that website has to authenticate the user, and once the authentication is done, it has to send the command to BCrouter. The user is authenticated. Just the user is logged in on that IP address, so that BCrouter knows it, and all traffic following that command will be accounted to both the user and IP address. So the authentication is, in fact, you can call it external to BCrouter itself.
Okay, thank you very much.
Hello, Andreas Polirakis from National Technical University of Athens. Do you have any numbers about the efficiency of this router? And, for example, how many users it can handle, or how many bandwidth it can handle? Are there any limitations?
Well, the only limitation there is for amount of users is the amount of system memory. So at the moment it was 40,000 users, 100 and something, 110,000 IP addresses. So it all maps to 150,000 objects, because user and IP is same principle from the bucket system. And each object has 2 buckets. So at the moment, with 1 gigabyte of RAM, you can have it's no problem to have 300,000 bucket systems in memory. Everything is programmed in a way that there are no linear dependencies on amount of users or amount of IP addresses. So
what about number of policies? I mean, if you have too many policies, does this affect?
There is a linear dependency there, but there are no problems up until, I don't think, 500 or more exception policies. But if it should be a problem, there are other solutions that also remove the linearity dependence on the amount of exceptions. So the exceptions itself are implemented in IP tables, but there are IP tables implementations that work based on binary trees instead of linear tables. And then there are no limits, because we have another firewall in production that has, I think, 6,000 or 7,000 IP tables rules, and it works perfectly.
What about bandwidth? Can it handle gigabit speeds and all this stuff?
Gigabit speeds is not a problem. So once the CPU is a limiting factor there, and it starts behaving weird, to say so, if the CPU load exceeds 59%. But the system we use is a system that is bought 3 years ago, so it's a rather old system. And especially with the new architectures like Core 2 Duo and AMD with the integrated memory controller, the current systems you can buy, just the normal systems, I think are at least a factor of 2 faster than the hardware we use. And yeah, I don't think there is a limit at the moment. If you want to achieve 10 gigabits, then there are possible some optimizations that can be done. But I think with normal hardware, relatively normal hardware, you can achieve 2.5 gigabits.
Okay, thank you.
Any other?
In terms of latency, can you do voice over IP through this? Can the students do Skype or other applications through this?
Latency itself, since it doesn't use a shaping algorithm, so it doesn't use wait queues to send the packets out on the network. The policing algorithm itself just determines accept or drop. So there is no significant extra latency besides a normal Linux router. It doesn't add extra latency, not measurable by me, in fact. So,
are there any other questions? So may I ask something? So under what license scheme is this software distributed?
It's meant to be open source, GNU license. But at the moment, it's still so hard in development and so hard to set up because there are no easy subscripts at the moment. I'm working on that. But once it's finished a little bit more, it will be released as open source, the full solution.
Are there any plans to introduce at least the kernel space thing into the mainstream Linux kernel?
No, not at the moment.
Okay, thank you very much. Thank you.
Also.
So we may proceed with the second presentation from Vangelis Aniotakis. We need a couple of minutes to set up. So as I mentioned before, Vangelis is going to present us a tool that is called an ANS tool, which has been developed in GRNet, and it is another tool also, AMPS, which is both of them are related to quality of service provision in IP networks. Vangelis.
Hi. Hi, my name is Vangelis Aniotakis. I work for GRNet in the University of Crete. And I'll be talking about the work we did about the interoperation between AMPS and the local GRNet developed ANS tool. Just an overview, we'll look at the objective of the work and a short introduction to QoS, which I'm sure most of you will be well aware of. The challenges we faced, a short description of AMPS, the QoS as it was developed in GRNet, ANS tool in general, and the interoperability specifics in the end. So, our objective was, in general, in all the service activities and joint research activity of GN2, is to provision end-to-end network services across multiple administrative domains, and insofar as this is possible, to use automation to do that, to cut down on delays, and service costs and administration. So AMPs and the whole this service we actually tried to automate is QoS. Now QoS, I just have to say these things. We have an increasing demand of QoS in IP networks. We have lots of multimedia in this with fast networks these days, and they need a better quality of service than the old model of best effort we used to have. We have voice over IP, we have teleconferencing. We do have lots of safety critical traffic. I mean, suppose surgery is done online or something like that. So we do need some quality of service. The main method that we implement QoS with is with diffserv, which means that there's lots of ways to do QoS. Diffserv is about assigning a class to packets, and it's coarse-grained. That means that the entire class of those packets is handled in the same way. The client is responsible to mark the outgoing packets in a specific field in the IP header. DSCP0 is usually best effort, and in GRNet we use some special values for previous class IP. The network is then responsible to respect those the EDS field after some admission control and forward them with a specific higher priority usually. So the scenario is very simple. In paper, we have multiple domains and two clients that want to communicate with some quality of service. So, but all these different domains may have their own way of doing QoS. Some may use different DSP values. Most will not will do some admission control and do not trust the EDS header, strip it and replace it with something else, or process the packet in different ways. They may or may not have resilience guarantees. They may provide multiple paths for a packet to go through or not. And the network core implementation of QoS may be different. GRNet uses MPLS, others do different sort of implementations. And more importantly, they may allocate different amount of bandwidth for each service type. Premium IP is the target service here, and GRNet allocates a certain percentage of its outgoing and incoming bandwidth to that service, and that may be enough for some applications, may not be enough for others, and we don't know if our peer networks will actually do the same as us. So if we have to do an end-to-end service across multiple domains, bear in mind this crosses probably 3 or 4 domains according to the resiliency we want to do. Everybody has to agree on a few things at least. So the AMPS system is about automating this provisioning. It was developed by the Giant SA3 service, that's Service Activity 3, and it means Advanced Multi-Domain Provisioning System. It's advanced because they do advanced reservation. You have to know in advance the service you will need, the endpoints and the parameters. It's not on demand quite yet. But we do have, I think we'll have very short response times eventually. Anyway, the architecture is, well, every domain, each one of those big boxes runs a few agents. First, we have an inter-domain agent. This handles most of the inter-domain communication with other peer agents of its type, and it also handles the UI for user interaction. And we have a network information agent that does pathfinding between domains and sometimes internally inside the domain. And we have an intra-domain agent that actually does all the work with QoS and provisioning and configures the network elements. All the agents intercommunicate using the SOAP standard with function calls over HTTP. So the interdomain receives a request from the end clients, sends and negotiates the parameters with its peers, and passes messages and so on. Will handle the status of a request
whether it was rejected or something happened and one domain couldn't handle it, and then it would do rollbacks and so on and so forth. And then it will call eventually the local intra-domain agent and use the local pathfinder agent, that's, well, the same as the network information agent, to determine what the next inter-domain agent will be to handle the request. We use a stepwise process. A request is given initially to one inter-domain agent, and then it discovers where else it needs to be forwarded. The inter-domain agent, it receives the provisioning request from the inter-domain agent, does some local pathfinding to determine the internal path it needs to configure. This is the vanilla implementation of AMPs uses traceroute to do that. We'll see how JRNet did this. And in the end, it will configure the nodes on the path to actually do the request. This may involve different implementation according to the domain, the technology specifics. The Pathfinder is an important but not quite user-friendly or evident agent. It looks at the local network database and decides what's the best path is to do about to use on implementing a request. Now, when you do QoS, you need to know which where the request will enter the network and it will exit the network. This is the ingress and egress node. You typically have to configure at least those nodes to handle the particular request. So, in the usual implementation, you have every link and reserve some bandwidth on it according to the service requested. So this was a bit sensitive because on transient failures, because traceroute will work like in one way right now, and in 5 minutes a node may fail and take a different path. And if you do a configuration change and move a line around, it will do different things, even if that was a temporary change. So when you submit a request, what you get may not be quite what you expected to happen. Okay, now QoS in JRNet is implemented. Well, this is a bit long slide, but it's an interesting topic. We allocate, we have lots of clients, they're academic networks, and we allocate in advance an amount of premium IP bandwidth to them. For small clients with a narrow connection, we assign a big percentage so they can fit something useful in there. And for big clients with gigabit connections, we assign a smaller percentage. Now, we pre-provision all this bandwidth in such a way that the core network can always handle the load. Even if some or many of our core network is offline, we can still handle premium IP traffic. This is an AppSec type problem, quite complex. JRNet has used some heuristic rules to come up with a solution, but this has a significant advantage because at the time of the request, we only need to decide whether the request is possible at the edge. We don't have to know anything about the core because the core is already configured as optimally as possible. This means that if one of our members asks for, let's say, 1 megabit of premium IP bandwidth and they've been allocated 5 megabits, we only need to know if this will fit with their other requests right now. And this also allows us to guarantee that if something fails, then that the network will always handle the load. I'm not too sure about the math about this. I wasn't the one who actually did all the work on that, but it's a fairly interesting subject available in the paper. Now, AMPS is not doesn't quite do things this way. It goes link by link, while we only look at the end nodes. So what we wanted to interoperate with the AMPS framework, and the only way to do that was to replace the AMPS intra-domain implementations and Pathfinder as well with our own. So to do that, GRNet already operates a topology database. This is more than a database. It's actually a whole suite of tools that we actually discovers network topology. It goes around and asks all the routers and switches and so on, and about the configuration, and writes all this down to a persistent database, and will allow for queries on it. The version 1, which has been in production for a few years, has a ad hoc schema, which was actually created as needed, and a plain SQL API, and was actually used to derive the network information database schema for AMPS. The version 2, which is heavily under development right now, has a unified schema with multi-layer topologies, and it looks like CNIS from JRA3, I think, from Jan 2. Is object-oriented both in its design and its API, and will have an XML API, and has geographical data integration and more. Everything is actually quite fluid right now, because there's lots of development going on. But we hope to have a rather nicer design than the first one. The ANS tool is now a web application that is built on top of the database. We use a UI for users to submit requests on network services. We communicate with the topology database to see if they're feasible, and we track the request along its life cycle. It may you create a request in advance, and then the time comes along for it to be implemented, then sometime it ends, or it may never get approved, and so on. And we produce automatically network configuration commands that you can simply copy-paste onto the routers. Now, we mostly use it for QoS and VPN services, and a fork of this ANS tool was adopted by HENet and is now in production, used for VPN mostly, and was renamed to BlueNet. We will have adapted ANS tool to do SOAP and map its internal commands to functions to SOAP functions. So what we did is we did exactly that. We adapted ANS tool to handle all the AMPS WSDL-defined user face, and mapped all the AMPS intra-domain calls to ANS tool commands. This this looks a bit like this. The ANS tool user interface, which is this is unlike the AMPS user interface. The AMPS user interface actually provisional just inter-domain request, while the ANS tool UI does both local and cross-domain requests. And we forward any requests that actually are cross-domain to the AMPS inter-domain agent. This calls us back, and after it negotiates, and hopefully when every agent has done its job, we will have a QoS that works. Now, the GRNet Pathfinder, let's remember that every request needs to know its ingress and egress node in the administrative domain. We need to redevelop it because we didn't really need to handle all the pathfinding that the AMPS Pathfinder does. We don't need to know every link, but actually we prefer not to. We just need to know where the request is coming from and where it is going from, and whether the service, there is available bandwidth to implement the service. We just, to find out exactly where we're coming from, where we're going, we just need to ask the core routers for which way the MPLS core is forwarding the packets, because we already know the client and the client, the endpoint IPs, and we just ask those. There's no need for us to actually do any trace route or anything else. And this will decide for us the ingress and egress. We do mostly at most 2 queries, and this is resilient because it doesn't rely on anything like the network actually being up when you ask it. Now, the AMPS client, this is the user interface. We replaced it because, well, we wanted to give the GRNet users a way to do giant calls for cross domains as well as local QoS requests in the same user interface. We use it as a SOAP client calling the AMPS inter-domain, the big one. And we use some wrapper functions that will map the local functions that we use to do a simple case switch, if then call the AMPS client. Now, okay, this is nearly over. Now, there were some more things we need to adapt. The local GRNet QoS was bidirectional in the service model. We assumed that everything would be symmetrical and that everything, well, it was a bit simpler, but it didn't work as AMPS was designed to accommodate unidirectional requests. So we had to change the local service model to do that. And we changed the UI logic to push the appropriate request to the AMPS inter-domain. And we wrote a SOAP server using PHP SOAP. All offense tool is written in PHP. We developed the Pathfinder from scratch. It's written in Perl and talks and speaks with the core MMP illustrators. And we did lots of testings. That was really kind of painful because you have lots and lots and lots and lots of calls across multiple layers in Java and PHP and Perl, and it's very, very, very hard to debug. A small bug can make everything go wrong. But we actually made it happen, and we've been able to have this as a production service in April. Now, well, Gian2AC3 developed the AMPS and funded the whole project. Angelos Varvitsiotin from GRNet was the main person who actually developed the topology database and Pathfinder module. He's very important in the whole scheme. And from the Computer Technology Institute, Dimitris Pimpas and Christos Bouras were behind the QoS implementation. I just did the SOAP things. Well, there's more information for you here. And if there's any questions, please go ahead.
Thank you very much, Vangelis. Are there any questions to this presentation? Okay, it seems that. So there is one.
Basically, I have 2 questions. The first one is about the granularity of the request. What kind of what is the granularity for the duration and the bandwidth the user can request? Well, the second question is also what is the users here? Is it a campus manager, a true end users?
Right now, there's AMPS is still in development. So I'll answer your last question first. The actual users are expected to be campus managers right now. There's no authentication or authorization infrastructure in place. So we will release this, I think, to maybe campus managers at most, and go from there. The users. The campus managers are expected to do the request on behalf of their users. Now, every request has a source IP and a destination IP, and the granularity of the and the service duration is measured in days or weeks or years. this is supposed to be about long-term reservations. It doesn't really make much sense to do something of that crosses 5 or 6 domains for a few minutes. Maybe if we had even more automation, that would be easier, but that's not the case right now. And well, I'm not sure. Did I answer your questions? Okay. And the bandwidth, yeah, that's also, you know, it's a few kilobits or a few megabits, or maybe a gigabit, or I don't know. There's no limit in that. Okay, thank you all very much.
Okay, we may shall proceed with the third and last presentation of this session. This is made by Vasiliki Pouli from the National Technical University of Athens. It's about end-to-end service level agreement provisioning and monitoring for end-to-end quality of service networks, IP networks. Vasiliki, I pass the floor to you.
Hello everyone, I'm Vasiliki Pouli from NCUA, and I'd like to present you a procedure as we have defined it in the EG project for providing end-to-end service level agreements for end-to-end paths that require specific level of quality of service across different resource centers. First, we will have an introduction, then we'll see of which parts the SLA can be comprised. Then we will describe the model for the SLA establishment as we have defined it. And then we'll present a procedure for the monitoring of these SLAs. Generally, in grid environments, when the grid applications requires a specific level of quality of service for some data transfers that can be made across different grid resource centers, then this quality of service has to be defined in an end-to-end SLA, which will provide all the technical and administrative details in order to perform the maintenance, the monitoring, and the troubleshooting for this data flow. So, the grid resource centers are the actual users of the network. But who are the network providers? In general, these are the GEANT, which is the Pan-European network. Also, we have the NRNs, which are the national networks, and in some cases, there are also the regional or metropolitan or campus networks. And due to the fact that the service provisioning is the responsibility of each administrative domain, each domain should provide its own SLA as seen in the figure below. So the end-to-end SLA across the path should be based on the SLAs provided from each individual domain, as we will see later. Now, the SLA, which part can comprise an SLA? We can divide an SLA into two parts. The first part can be the ALOB, the administrative level object. This part can contain administrative details, such as some point of contacts, the duration of the service, start and end times, the availability of the service, let's say which days of the week the service is really available, some response times. These are the domain acceptance response time, which is how many days it needs to respond to a request, and it's also the reservation request lead time, which is how many days you need to do a request before the actual service reservation can be provided. And also we have to describe some fault handling procedure in case of faults. The second part of the SLA can be the service level object, which is an object describing the technical details concerning the specific service flow. You can also provide some how the excess traffic can be treated, and in greater importance, there are the performance guarantees that you should describe. These are the one-way delay, the jitter, the packet loss, capacity, and also some reliability guarantees should be described, which are the maximum, the allowed maximum downtime in the service duration, and the allowed maximum time to repair in case of downtime in the service provisioning. Also, in order to monitor these, the above guarantees, you should also provide the monitoring infrastructure, meaning you should provide the monitoring capabilities of each domain in points of where the measurement points are possible, the availability of these measurements, if they are on demand, if they are per cases, if they are continuous, the granularity of these measurements, the time intervals, and also you should provide a methodology for the statistical processing of the measurement data. Due to the fact that we are dealing with multi-domain SLAs, we need a trusted third party which will be responsible for the SLA installation, for the SLA management and monitoring, and generally it will provide the user support for any network-specific issues that may arise, such as network SLA violations. For the DG project, this trusted third party is the NOC. It's DG Network Operations Center. It's something like the counterpart of NRN NOC, but it's for DG. And it's in charge of DG network operations, such as the detection and resolution of problems, handling of notifications coming from the NRNs, and network monitoring and SLA management in general. So after we have some introduction, we will proceed to the description of the model for the SLA establishment. At first, we have preliminary agreements between the NOC and the participating domains and the resource centers. This is made once for every participating domain and resource center. And its scope is to, for the domains to state how much bandwidth they will allocate for DG, and for the resource centers to state that their provisioned resources, network resources, will be used only for EG purposes. All this information is received by the NOC, and it's gathered, it's stored in the network operational database, which also stores topology information for the network. After the preliminary agreement, for every service request, we have a two-stage provisioning model. In the first stage, we have the service reservation, and in the second stage, we have the service activation. In the service reservation, we have a reservation of the service in the extended Quota network. This is the GEANT and the NRNs. And from the SLAs that these domains will provide, we will define the border-to-border SLA. This is the first part of the end-to-end SLA. And in the service activation stage, which is this stage happens when the actual activation of the service needs to take place. We have the configuration of the routers in the last mile networks, and we have the provision of the end-to-end SLA across the path, which will be provided by the border-to-border SLA provided from the first stage, and from the SLAs provided from the NRN client domains. We will see these phases, stages in more detail afterwards. Why do we have this two-stage provisioning model? Generally, the grid applications require that the end-to-end network path be available in time. This cannot be happen so easily because there's a lead time between the service request and the service reservation in the extended course network, in the GEANT and in the NRNs. Because currently there's manual configuration of the routers. So we need 2 working days in order to make a request and to reserve the GEANT and the NRS network. So now we'll describe each stage in a greater detail. The first stage, the service reservation stage, has 2 cases depending on whether the reservation can be made in an automatic or a manual way. In the automatic way, the reservation can be made by the AMP servers of the hosting NRNs and the GEANT. The AMPS is the Advanced Multi-Domain Provisioning System. It's a system currently in development stage by the GEANT project, and it manages the whole premium IP provisioning process from the user request till the configuration of the appropriate network elements. It can provide the scripts, the configuration scripts for the routers, which are then manually installed to them. The manual reservation is when no AMP servers or similar services installed in the NRNs, so the reservation should be done in a manual way. Now, the service reservation procedure can be described in the following flowchart. We have the SR actor, the service request actor, that makes a request for an SLA service to the NOC, and the NOC has to retrieve information from its database, its network operational database, in order to see if this request is within the maximum bandwidth agreement boundaries of the bandwidth that its domain has provided. If it is, then it forwards the request to the first AMP server of the end-to-end path, and the AMP server either accepts the request or no. If the reservation cannot be reserved in the time period that the user defines. If the AMPs accept the request, then the NOC has to contact the involved domains and ask from them to complete their SLAs, which are then merged into the border-to-border SLA and stored in the network operational database. So on this stage, we have the border-to-border SLA coming from the SLAs of the GEANT and the NRNs. In the manual reservation, this is the case where, as we said before, no AMP servers or similar services are installed in the NRNs. So the difference here is that the NOC has to initiate manual requests in its domain in order to ask if they can accept the request. And again, if the domains can accept the request, they provide their SLAs, which are again merged into the border-to-border SLA and stored in the network operational database. Now, the second stage takes place when the actual reservation activation of the service needs to be done. So in NOC, as we see in the flowchart, verifies and retrieves the reservation done from the extended in the extended course domain, and checks if it's still effective. Then the NOC should ask the NRN client domains if they can, meaning the campus and institution networks if they can accept the request. And if they do, then they provide their SLAs, which are forwarded to the INOC, and INOC produces the end-to-end SLA for the end-to-end path, which is based on the reported SLAs from the NRN client domains, along with the border-to-border SLA gathered from stage 1. In order to monitor these SLAs, the INOC has to query the network performance and monitoring diagnostic tool. This is a tool that is provided by the EG project and provides measurement data from the perf owner and the E2E monitoring frameworks. The first monitoring framework is used mostly for bandwidth measurements, and the E2E monitoring framework is used for end-site to end-site measurements of delay, jitter, packet loss. By these measurements, INOC has to check if the SLA guarantees are honored, and if in case of faults or a notification comes in from either the user or the NRNs or the participating domains, the INOC tries to identify either by taking intermediate measurements or by the measurement that gathers from the monitoring frameworks, tries to identify the responsible domain and notify it in order to troubleshoot, or in case that the problem cannot be isolated, then it has to inform the GEANT PERT, it's the Performance Enhancement Response Team, and together try to identify and troubleshoot the problem. In each domain has to troubleshoot according to the fault handling procedures defined in the SLA, and when they troubleshoot, they should report back to the INOC, and INOC has to make time cross-checking of the response times against the promised ones in the SLA. In order for the SLA monitoring to be effective, the following requirements should be provided. We need to monitor some end-to-end metrics, performance metrics mostly. These are the one-way delay, the IP packet delay variation, the round-trip time, packet loss, the available and achievable bandwidth, and also we need to measure the reliability of the service, meaning that the time to repair, which is the time from reporting a problem till its recovery per every metric violation, and the allowed maximum downtime, which is the maximum total of all the times to repair for all the violations in a given period, which is less or equal to the SLA period. All this must be somehow measured. Also, in order for these metrics to be monitored, we can some monitoring features can enable the monitoring to be more effective. These are the frequent end-to-end and partial domain monitoring of the performance metrics that I described before. Let's say we have to make frequent measurements every 15 minutes or so in the agreed service availability period. Then also we have from the monitoring frameworks, it should provide us with the capability of setting thresholds on the metrics that we want to measure and generate alarms in case of violations of these metrics. We can also define different severity levels for the different severity of each violation. Also, the trouble tickets triggered either by the users that see a degradation of the performance of the service or by the NOC operators in case of alarms will be managed via the trouble ticket manager. And finally, statistics from these trouble tickets will be used in order to infer the maximum downtime and the time to repair. That's all I had. Thank you for your attention. If you have any questions, you can raise them.
Thank you, Vasiliki. Nice to see this correlation between these two big projects, namely Xeant and GE. Are there any questions? So more or less then we conclude with this session. I would like to thank you all for you attending this first session of the arena. I would like to wish you to enjoy your staying here in Copenhagen and have a fruitful meetings with other networkers the next days. Thank you very much, everybody.